Beneath the vast, seemingly desolate landscapes of Siberia lies one of Earth's most critical carbon vaults, the permafrost. For millennia, these permanently frozen soils have locked away ancient organic material, creating a natural carbon sequestration system that has remained stable throughout human civilization. But today, this frozen archive is unraveling at an alarming rate, catching even the most pessimistic climate scientists off guard. Join us as we explore how this remote region may be triggering one of the first observable climate tipping points, with consequences that will reach far beyond Siberia's borders. Siberia's vast permafrost has functioned as Earth's most efficient carbon vault for millennia. This natural freezer has locked away ancient organic material since the last ice age, maintaining a delicate equilibrium that has remained largely stable throughout the development of human civilization. But this balance is now unraveling at a pace that has alarmed climate scientists worldwide. The permafrost, once considered a static feature of Earth's cryosphere, is revealing itself to be dynamically responsive to our warming world, with consequences extending far beyond these remote landscapes. The Yedoma permafrost region is particularly significant, a unique ice-rich geological formation spanning approximately 1.4 million square kilometers across northeastern Siberia. This region represents one of the planet's most concentrated carbon repositories, containing not just carbon but a complete paleobiological record. Preserved plant matter, ancient microorganisms, and organic compounds that have remained unchanged since woolly mammoths roamed the region. As this frozen archive begins to thaw, it's not just releasing greenhouse gases. It's reanimating an ancient biological world with unpredictable consequences for our modern climate system. In April 2023, researchers from the Permafrost Carbon Network documented a deeply troubling phenomenon across Siberia's Yedoma permafrost region. Using advanced airborne measurement techniques, they recorded methane emissions a staggering 42% higher than their 2020 baseline measurements. According to previous climate models, this dramatic increase wasn't expected until the 2040s. We're witnessing changes decades ahead of schedule. The Yedoma permafrost contains approximately 130 billion tons of organic carbon that has remained frozen for tens of thousands of years. What makes this development particularly concerning is the detection of what scientists now call methane pulse events, sudden releases exceeding 150 kilograms per day from relatively small areas of less than 1 square kilometer. These events were recorded at 17 different regional sites, suggesting this is a systematic phenomenon rather than isolated incidents. The largest pulse, measured near Lake Kamra, released approximately 280 kilograms of methane in just 24 hours. The international research team, led by Dr. Katie Walter Anthony, employed cutting-edge techniques previously unavailable to permafrost researchers. Their methodology included aerial infrared thermography to identify hotspots and drone-mounted laser spectrometers to quantify emission rates with unprecedented precision. This technological advancement has revealed that previous ground-based measurements significantly underestimated both the volume and variability of methane releases from thawing permafrost. The temporal pattern of these methane emissions adds another layer of concern to the permafrost crisis. The research team discovered that these methane pulses demonstrate a distinct diurnal rhythm, with emission rates increasing by up to 60% during afternoon warming cycles. This suggests that even minor temperature fluctuations can trigger substantial methane releases once certain thresholds are crossed, a troubling indication that the system has become highly sensitive to thermal changes. This sensitivity points to a permafrost system that has become increasingly unstable and reactive to environmental conditions, potentially creating feedback loops that could further accelerate emissions. The relationship between daily temperature cycles and methane release rates provides valuable data for climate scientists, but also underscores how quickly the situation is evolving. These observations indicate that the permafrost is not gradually degrading as previously thought, but responding dynamically to temperature changes in ways that amplify its greenhouse gas contributions. Traditional permafrost thaw models projected a gradual top-down melting process, but recent observations reveal a more complex and troubling mechanism called abrupt thaw. This process begins when surface water accumulates in small depressions created by initial thaw. These water bodies absorb solar radiation more effectively than surrounding surfaces, creating thermal hotspots that accelerate melting beneath them. Dr. Marit Turetsky, director of the Institute of Arctic and Alpine Research, recently identified how these thaw processes create what she terms thermokarst failures, sudden collapses in permafrost structure that expose deeper layers to warming. The most concerning discovery from the 2023 measurements was that abrupt thaw appears to be initiating at depths of 3 to 5 meters, where particularly carbon-rich layers exist in Yedoma formations. Unlike carbon dioxide, which remains in the atmosphere for centuries, methane breaks down within approximately 12 years. However, it has 84 to 86 times the warming potential of carbon dioxide over a 20-year period, making these sudden releases particularly potent climate forcers in the near term. The mechanics of thermokarst formation involve complex hydrological and geomorphological processes that are rapidly reshaping Siberia's landscape. As the ice-rich permafrost thaws, the ground surface subsides, creating depressions that fill with meltwater. These newly formed thermokarst lakes then accelerate thaw beneath and around their perimeters through thermal erosion and wave action. The resulting landscape transformation can be dramatic. Satellite imagery from the Yakutsk region shows areas where the surface topography has been completely restructured over just 7 years, with forests transformed into lake-dominated wetlands across hundreds of hectares. What's particularly alarming about the abrupt thaw phenomenon is its capacity to bypass the insulating effects of the active layer, the shallow surface zone that typically thaws and refreezes annually. By creating direct thermal pathways to deeper permafrost, abrupt thaw processes can mobilize carbon stores that would have remained stable under gradual thaw scenarios for many additional decades or even centuries. This means carbon that climate models assumed would remain locked away for generations is now being released into the atmosphere, accelerating climate change beyond previous projections. Perhaps the most surprising element of the recent findings involves microbial communities being reactivated after millennia of dormancy. The Russian-American Permafrost Microbiome Initiative published findings in March 2023 documenting how methanogens, microorganisms that produce methane, are not merely surviving the thaw but thriving in it. Their research identified previously unknown strains of the Methanobacterium genus, demonstrating unusual adaptive capabilities. These microbes can transition from dormant states to active metabolism within 30 to 45 days of thawing, significantly faster than the 1 to 2 year activation period previously documented for permafrost microbiota. More concerning, these particular strains show peak methane production at temperatures between 5 to 10 degrees Celsius, precisely the temperature range that characterizes newly thawed permafrost zones. Dr. Yelizaveta Rivkina from the Russian Academy of Sciences Institute of Physiochemical and Biological Problems in Soil Science noted that these microorganisms represent functional ecosystems preserved in a frozen time capsule, with metabolic pathways optimized for carbon-rich environments that no longer exist in most of Earth's surface biosphere. The genomic analysis of these microbial communities revealed another unexpected finding. Horizontal gene transfer occurs at accelerated rates within thawed permafrost environments. This suggests that these ancient microorganisms rapidly share genetic material that enhances their metabolic capabilities in newly thawed conditions. The evolutionary implications are profound. We are witnessing real-time adaptation of organisms that evolved in the Pleistocene as they encounter the Anthropocene. Metagenomic sampling across different thaw stages has identified a clear succession pattern. Aerobic decomposers initially dominate newly thawed material, followed by a rapid transition to anaerobic communities dominated by methanogens within 60 to 90 days. This succession occurs much faster than predicted by laboratory studies, suggesting that in situ conditions provide currently unidentified factors that accelerate this transition. This microbial adaptation represents a previously underappreciated aspect of the permafrost carbon feedback loop. Not only is carbon being released, but ancient microorganisms are evolving to process it more efficiently, potentially accelerating greenhouse gas production beyond what current models predict. The implications of Siberia's thawing permafrost extend far beyond the region itself. The International Permafrost Monitoring Network has begun incorporating these findings into next-generation climate models, with troubling preliminary results. Their initial recalculations suggest that permafrost feedback loops could contribute an additional 0.3 degrees Celsius of global warming by 2100, a significant fraction of the remaining carbon budget for keeping warming below the critical 1.5 degrees Celsius threshold established by international climate agreements. More immediately concerning is the discovery of what climatologists call reinforcing heterogeneities, situations where localized warming triggers changes that accelerate the warming process. For example, when methane release leads to local vegetation changes, those new plant communities often have lower albedo, reflectivity, absorbing more solar radiation and further accelerating thaw in a vicious cycle. These cascading effects can create hotspots of rapid change that might spread across larger areas over time, potentially triggering regional-scale transformations that current models struggle to predict accurately. The most recent data from the Siberian permafrost region suggests we may have crossed tipping points in at least some permafrost systems decades earlier than anticipated. As Dr. Turetsky soberly noted in her April 2023 presentation to the European Geosciences Union, we're no longer discussing if permafrost will cross irreversible thresholds, but rather which thresholds have already been crossed and what that means for both regional ecosystems and global climate trajectories. The modeling challenge is substantial, as current Earth system models still struggle to represent the heterogeneous nature of permafrost landscapes and the non-linear dynamics of abrupt thaw processes. The latest generation of models developed by the Permafrost Carbon Network includes a finer-scale representation of hydrological processes and microbial dynamics. Still, significant uncertainty remains about accurately scaling localized pulse events to regional emission estimates. This uncertainty doesn't diminish the urgency of the situation. Rather, it underscores the need for more comprehensive monitoring and improved modeling approaches to better understand the rapidly evolving permafrost dynamics. The accelerating methane release from Siberia's permafrost represents more than just another climate feedback loop. It embodies the complex, nonlinear nature of Earth's response to human-induced warming. The emerging data challenge our understanding of climate system timelines and highlight the potential for rapid transitions that outpace natural adaptation and human response capabilities. For climate policy, these findings underscore the urgency of immediate emission reductions. The permafrost feedback is now clearly operational, not theoretical, and appears to be accelerating faster than anticipated. This suggests that the remaining carbon budget may be smaller than current estimates, and that the window for effective climate action is narrowing more rapidly than previously understood. The Siberian permafrost situation also highlights the importance of maintaining comprehensive Earth observation systems. Detecting methane pulse events was only possible through advanced monitoring technologies deployed through international scientific cooperation. Maintaining and expanding these monitoring networks, particularly in remote regions like Siberia, must be a global priority despite geopolitical tensions. As Dr. Walter Anthony emphasized in the conclusion of her recent paper, what we're witnessing in the Yedoma region may represent one of the first clearly observable climate tipping points in action. The challenge is determining whether intervention strategies exist that could slow or stabilize these processes, or whether we must accelerate adaptation planning for a warmer world arriving faster than anticipated. This sobering assessment captures the essence of the permafrost crisis. We are witnessing a planetary system transformation in real time, with consequences that will reverberate through global climate systems for generations. The accelerated timeline of permafrost thaw has caught the scientific community by surprise, forcing a reevaluation of climate projections and adaptation strategies. The question now is not whether significant permafrost carbon will be released, but how much and how quickly, and whether human societies can adapt to the resulting climate changes. The Siberian permafrost crisis serves as a powerful reminder that Earth's climate system contains thresholds and tipping points that, once crossed, can lead to rapid, self-reinforcing changes beyond human control. Siberia's permafrost crisis represents a critical inflection point in Earth's climate history. What was once a stable carbon repository, preserving ancient organic material for millennia, has transformed into an active contributor to atmospheric greenhouse gases at a pace that has outstripped scientific predictions by decades. The discovery of methane pulse events, abrupt thaw processes, and the reactivation of ancient microbial communities paints a picture of a system in rapid transition. These changes are not merely academic concerns. They represent a significant narrowing of our window for climate action and suggest that global warming may accelerate beyond current projections. The permafrost feedback loop has moved from theoretical to observable, from future concern to present crisis. As we witness one of Earth's largest carbon vaults unlocking before our eyes, the urgency for both mitigation and adaptation strategies becomes undeniable. The Siberian permafrost may well be showing us our climate future, arriving much sooner than we expected. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.